Right, Miss Howard's pre-AP chemistry class, we're talking about stoichiometry. Stoichiometry is the math that goes along with balanced chemical equations. I know you're so excited. Alright, so let me remind you of a few things, like how big is a mole. If you had 1 mole of marbles, you could cover the entire Earth, oceans included, for a depth of 2 miles of marbles. Think about that. Remember, that mole, when you have 1 mole of something, you've got 6.02 times 10 to the 23rd particles, and that's just almost an unimaginable amount. 1 mole of dollar bills, stacked one on top of each other, would reach from the Sun to Pluto and back 7.5 million times. Although Pluto's not a planet anymore, I don't know if it'll do that again. It would take about 9,500 light years to travel from the bottom to the top of a stack of 1 mole of dollar bills. Remember a light year? How far light can travel in 1 year? That's pretty amazing. So again, we're just emphasizing how big that number is. And it has to be that big because atoms and molecules are so incredibly tiny that you've got to get huge numbers of them to actually be able to handle them in a lab reasonably. Oh, love marbles. Amadeo Avogadro. Avogadro's number, 1 mole of anything has 6.02 times 10 to the 23rd particles in it. And look at that, all those zeros. Or 6.02 times 10 to the 23rd. And again, we already did this in class before. We talked about thousands, millions, billions, trillions, quadrillions, what is it, pentillions? That doesn't sound right, does it? But you guys can correct me. Okay, so looking at your notes, let's make some cookies. And you can kind of think of stoichiometry and a balanced chemical equation as like a recipe for something. When you're baking cookies, a recipe is usually used, telling the exact amount of each ingredient. If you need more, you can, whoa, what happened there? Let's go back and try that again. Oh, my goodness. All right. I kind of, okay, sorry. When making cookies, we can, no, we don't want pointers. We can double the recipe, we can triple the recipe, we can halve the recipe in case you're not feeling the need for lots of cookies, you can cut it in half. So you can do that by looking at the ratios between all the substances that you're working with. So a recipe is kind of like a balanced chemical equation. We can have a balanced chemical equation where you've got 2 moles of one substance has to combine with 1 mole of another substance, and we can cut that in half. We can say, oh, well, we're only going to use 1 mole of this substance and half a mole of the other one. Well, when you talk about stoichiometry, that's what you're dealing with. It's Greek for measuring elements, or it's pronounced stoichiometry. Stoichiometry. Say that 3 times really fast. It's defined as the calculations of the quantities in chemical reactions based on a balanced equation. Quantities. So this is where we really heavily start a lot of the calculations in pre-AP chemistry, and it's not going away from here. There are 4 ways that you can interpret a balanced chemical equation. 4 ways. Are you looking at your notes here? 4 ways. You can think of it in terms of particles. An element's made of atoms, a molecular compound's made of molecules, and an ionic compound would be made of formula units. But you can think about it in terms of particles. So by particles, again, you can think how many pieces are there. So we can use Avogadro's number and think of it in terms of particles. So again, elements are made of atoms. Whoa, what happened here? I put my paper down on my little bamboo thing over here. It doesn't like it so much. Let's go back. All right. A molecular compound, remember, that's a covalent compound made of nonmetals bonded together. Have I mentioned that to you multiple times yet? Yeah. Right. So a molecular compound is made of molecules, and then the ionic compound made between a non-metal and a metal is going to be made of technically formula units or ions. So they've got different names for these. Alright, so here we have a balanced equation. 2H2 plus O2 yields 2H2O. That's a baby equation. You should know that one easily. 2 molecules of hydrogen, 1 molecule of oxygen form 2 molecules of water. So we can think of it in terms of particles. We have the next one here. We have 2 aluminum oxides, 2 molecules or formula units of aluminum oxide, and that breaks down, decomposes to form 4 atoms of aluminum plus 3 molecules of oxygen. And that's exactly what it says right there. Oh, look. I've already balanced the equation for you. All you have to do is copy it down. What was I thinking? Okay, now try this one. We have what? 2 atoms of sodium plus 2 molecules of water. And you have, what kind of reaction is that? That would be a single replacement reaction. And you produce 2 formula units of sodium hydroxide and 1 molecule of hydrogen. Okay, now, you can also, besides thinking about it in terms of particles, you can also think about it in terms of moles, because those coefficients in front of there can stand for moles. So if you, and this is more realistic in the lab, we take 2 moles, because we can convert moles to grams and find out how much to measure out in the lab. We can have 2 moles of aluminum oxide, and it's going to decompose to form 4 moles of aluminum and 3 moles of oxygen. 2 moles of sodium plus 2 moles of water produces or yields 2 moles of sodium hydroxide and 1 mole of hydrogen. Now, do the moles stay the same on each side of the equation? No. You've got 2 moles and 2 moles on the left, so that's 4 moles on the left, and 2 moles and 1 mole on the right. It's not the moles that are conserved in a chemical reaction. When we talk about the law of conservation of mass, it's mass that's conserved. Or we can count atoms and say, okay, atoms are conserved. We haven't, or particles. You can say, hey, these particles haven't gone away. These little pieces of atoms haven't gone anywhere. So moles don't have to be conserved. It's mass that's conserved. The coefficients here tell us how many moles of each substance are there. Let's see. Then a balanced equation is actually a molar ratio. Kind of like you can say, oh, well, this recipe calls for 1 cup of flour to 2 cups of milk and 1 cup of sugar. So you have a 1 to 2 to 1 ratio. So a balanced equation is showing you that the mole ratio that's there. Okay, now the law of conservation applies always, always, always. So we can think about this balanced equation in terms of particles, in terms of moles, and also in terms of mass. Now, it doesn't have the mass listed in the balanced equation, but you know how to convert moles to grams, so you can do that easily. So the law of conservation is going to apply here. We can check it using the moles. So if we have this basic equation for making water, we can say, okay, we've got 2 moles of H2. So we have 2 moles of H2, and we have 1 mole on bottom for every 2.02, and in this case, you know, they didn't round like I've told you guys to, grams of hydrogen. So we convert moles of hydrogen to grams of hydrogen, and we find that we have 4.04 grams of hydrogen, and we can do the same thing for the oxygen. All we're doing is converting moles to grams. Right? Now, why does it say 32 grams of oxygen instead of 16? Because it's not just oxygen by itself, it's O2. So there are 2 of those. So if we look at that equation, we started out with 32 plus 4.04. We started out with 36.04 grams on the left-hand side of the equation. 36.04, right? So how many grams are we supposed to end up with on the right-hand side of the equation? Yes, children, you are right. The same amount. So again, we added up to 36.04 grams of hydrogen and oxygen total. And then we can say, okay, we've got 2 moles of water, and we convert that from moles to grams. And sure enough, we get 36.04 grams of water produced. So it's the mass that's conserved on both sides of the equation. So we started out with 36.04 grams, and we ended up with 36.04 grams. The mass of the reactant is always, always, always going to equal the mass of the products. That's what that young Antoine Lavoisier came up with. Who was Lavoisier? Wasn't he the father of chemistry? I think he was. Okay, so we can think about it in terms of particles. We can think about it in terms of moles. We can think about the balanced equation in terms of mass. And, this is new for you guys, we can also think about it in terms of volume of a gas. It only applies to gases, so volume of a gas, and it only applies to a gas that is at STP. STP stands for standard temperature and pressure. STP is a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. So, oh, look at this. Hydrogen, pure hydrogen is a gas, right? And also pure oxygen is a gas, so we can apply this. So, if, according to Avogadro, yes, that's the Avogadro, he said that, hey, if you have 1 mole, or if you have a certain amount of any gas, it's always going to have the same number of particles, no matter what gas it is, as long as it's at STP. So we have 2 moles of the hydrogen gas, and since it is at STP, it's like saying, hey, 2 times the 22.4 liters. We have 1 mole of the oxygen gas, and it's at STP, so it's like saying, hey, we've got 1 times the 22.4 liters. Now, if we made, and we're pretending that we made water and it's in a steam form, it's not in a liquid form, we've got 2 moles of that, and so we have 2 times 22.4 liters. So we can use that also as a way to convert from moles of one substance to moles of another. Right. The mass and the atoms, again, are always going to be the same on both sides. The yield on both sides of the yield sign. However, the molecules can change, right? The formula units, the moles and volumes will not necessarily be conserved. They aren't going to remain the same. It's possible accidentally that they'll remain the same, but it's not on purpose. Atoms are conserved because you can't obliterate atoms from the universe doing normal chemistry. And mass is conserved, not the number of moles you have. Okay, here is your first practice. Show that the following equation follows the law of conservation of mass. And you need to show that the atoms balance and that the mass on both sides is equal. So it's easy to show that the atoms balance because you can look and say, oh, look, 2 aluminum oxides. So we have 2 times 2 is 4. We've got 4 aluminums. 2 times 3 is 6. We've got 6 oxygens on the left. It decomposes into aluminum and oxygen gas. And we have 4 aluminums on the right, and 3 times 2 is 6. 6 oxygens on the right. Oh my goodness, that's all for the first one. Let's see if we can stop recording.